Indeed.
And I have to also congratulate you. You have the longest abstract so far in the seminar series also.
Yes!
Very good.
Great achievement. Thank you. Right. Well, thanks so much to the organizer. It's great to be here to talk about the SCR hierarchy, which is a program that I can describe as the closest thing that I have to a third child. So this is something that we care a lot about. This is joint work with a lot of people. So this is a happy mix of, let me see if I can get this to work, yes. This is a happy mix of students, former students, postdocs, former postdocs, and friends. So Alex Bastunis, Simon Becker, Jonathan Benarsi, Matt Colbrook, Olava Nevelina, Bogdan Roman, Marcus Seidel, and Werner Vlacic. And instead of me standing here giving you a very long monologue about how important it is to care about foundations of computations, I'm going to start with 3 examples. I'm going to start with the computational spectral problem. And I don't think I'm going to be too provocative if I suggest that this is one of the core problems in numerical analysis and scientific computing, and that this has been investigated intensely over the last half century. I've just compiled a list of people who have contributed to this. If you have done spectral computations and you're not on this list, please don't be offended. This is not like a top 10 list of people in the field. Pardon me? No, actually, the purpose of this compilation is just to show you the wide range of people. Because you'll find people like Schrodinger and other distinguished physicists like Schrodinger, and you'll see also very prominent pure mathematicians, and you'll recognize some very prominent applied mathematicians. So this is something that has been investigated quite substantially. So it's fair to say that this has fascinated mathematicians and physicists for a long time. But it has also frustrated them. So if we simply ask the question in the simplest form I can think of, I have an infinite matrix, and I would like to compute the spectrum of that. Can you do it? And as Bill Arvidsson pointed out in the mid-90s, Arvidsson was a very prominent operator theorist at UC Berkeley. He did some really fundamental work on C-star algebras and numerical analysis in that time. And as he pointed out, there's a dearth of literature on this basic problem, and so far we've been able to tell there are no proven techniques. And the issue is not easier if we go to even more narrow classes of operators. So slightly paradoxical, we have Schrodinger operators here, and if we simply ask, can you compute the spectrum of a Schrodinger operator with a bounded potential, and actually C doesn't matter, I can put C infinity with whatever bounds on the derivatives, doesn't matter. 90 years of quantum mechanics, we still don't know how to compute spectra of a Schrodinger operator of that form. So this was the first example, and of course I'm going to get back to these and link them to the SCI hierarchy. But now I'm going to shift gear and go to a completely different problem, namely linear programming. And I'm also going to make the claim, which is probably not too controversial, that this is also one of the most investigated numerical problems over the last half a century. You all know it very well, and we're interested in solving a linear programming of this form. And I'm simply posing the problem of finding an algorithm that computes a minimiser. And if I ask that for a linear program, you probably think that I slipped in my bathroom this morning and hit my head very badly. Because how on earth can I ask about if you can solve a linear program? That's nuts. The key thing that I would like to point out is that I'm interested in minimizers. And mathematics of information now has changed the demand of problems in optimization. It's not the objective function anymore. It's the minimizers. So while you might still think that I'm nuts asking if you can actually compute linear programs, I'm going to start with a little MATLAB test to illustrate the issue. So I'm going to test MATLAB's routine, which is called linprog, which is a basic routine for computing linear programs. Linprog has a very nice feature. It has an exit flag. So this exit flag here is going to spit out a number, and it gives you the number 1 if the algorithm is happy with the solution, and a bunch of other things if it's not happy. Right now, I don't care what the other things are. I'm only interested in 1 or not 1. So I'm simply going to test it. I cooked up a very innocent little linear program. Here is my A. It's a 1 by 2, so I cannot cook up anything simpler. The Y is 1, and the C vector is 1, 1. And I'm going to plug that into the command line prog. I know what the true solution is, so I can compute the error, and I can, of course, get the exit flag. And here's the output. I do pretty well in the beginning, and then at the end, I get complete nonsense. But
The solution is this x, what? Okay, again. So what is the true solution?
the true solution here is 0, 1.
Yeah, all right.
So I don't actually show you what it computes, I just showed you the error. So in the beginning, I'm getting 10 digits. That's OK.
So the x is different to the x minimizer, right?
Oh, this x is varying over this. That has nothing to do with the minimizer.
Yeah,
Yes. I'm varying this over different. Yes. Yes. Yes, I agree. Anyway, I'm getting complete garbage here. And, well, that could happen, but at least this is where the exit flag is going to come and save the day and show us that everything is fine, because at least it's going to verify this as, well, oops. It actually verifies the nonsense as a correct solution. And now things become a little more interesting. So the first question that we can ask is this because Cleve Moeller hired a bunch of incompetent people in MathWorks? Or the second question, is it more deeper? And of course, we're going to relate this to the SEI hierarchy later on. You may think, what on earth is really going on here? Because, first of all, it is true that you can solve linear programs. Danzig did that for us. You can do that with the simplex algorithm. You can even do this with much faster algorithms, Karl-Marx's algorithm, or any of the other interior point methods that are on the market. But here is the catch. You can solve linear programs over the rationals. And it's true that it's a polynomial in time with the following estimate. N to the 3.5, where n is the number of variables, and L is the number of digits that you have in your input. And this is the key issue. And we're going to get back to this a little later on. Right. So that was example number 2. Now we're going to do example number 3. Polynomial root finding. Also an example that I don't think I'm going to be too provocative if I suggest that this is also a core part of modern numerical analysis and has been investigated substantially. What you do if you would like to compute the root of a polynomial. There's tons of different ways of doing it. One is Newton's method. And if you teach basic numerical analysis or undergraduate calculus, you may teach Newton's method. And it's not too hard to show that it doesn't converge. You can just do a cubic. So Steve Smale started asking some quite fundamental questions about existence of algorithms and a potential alternative to Newton's method. This was done in the mid-80s. And this is sort of the beginning of his program on foundations of computational mathematics. So Smale simply asked, does there exist an alternative? Can you cook up some other rational map, not Newton's method, so that you iterate on the complex plane and you get a root over a polynomial? So this question at the time was picked up by at the time, young and up-and-coming mathematician who was then a student at Harvard. This is his thesis. You'll have to pardon my slight simplification of his theorem. The whole paper is actually that theorem. But I encourage you to read it. So, pardon me. So the starting values that you're going to iterate on.
So open and dense, what is it?
Pardon me?
Open, dense.
So I do the completion, I get the whole C.
What is open? I know what the dense is. What is open, dense?
So I make the closure of the open set, I get the whole thing. So the answer to that is no, but there's more to be done. So what McMillan did, continuing, he was a postdoc at Princeton when he did this and collaborated with Peter Doyle, who was also a junior faculty member at the time. So he showed that you cannot do this in general. You cannot find another rational map that can solve, iterate on the complex plane and give you the roots of a polynomial. But what he showed with Doyle was that you could do this in the case of the quintic in several limits. So you would start by taking a rational map that will iterate, and it will produce some output that could go into a second mapping, iterate again, third one, that guy becomes a root. And the reason why this is fascinating is that it shows a very peculiar example in numerical analysis that there are problems for which you cannot actually solve by just passing to a limit. You need several. This is a very deep result, and for those who are interested in the historical perspective, it was actually cited by the Fields Medal jury when he got the medal in '98. So, these were the three examples that I want to start with as the motivation for this talk. And I'm going to talk about this Solvability Complexity Index hierarchy, which sounds like completely abstract nonsense. What I need to do now is to give you a little bit of an introduction to this. So it's going to be a little dry in the beginning, but I can promise you it's going to be party on when we're done with the dry stuff, because then we're going to use it. And the purpose of this is not to make numerical analysis and scientific computing essentially overly abstract and complicated. The purpose here is actually to solve problems and make things easier. So what is it? I just want to mention that this program sort of started with a paper in 2011, but we have essentially been able to mature this now much more substantially. The purpose of the program is to establish the foundations of computational mathematics. And that means that we need to be so general that whatever you can define as a computational problem, you must be able to encompass this into our definitions. So the abstract nonsense is there to ensure generality. So this is what we mean by a computational problem. I have my input set omega. That is going to be the class of problems I'm interested in computing with. Say a bunch of matrices for which I may want to compute the spectrum. Could be a class of linear programs, type of Schrodinger operators, whatever PDE you want, something that you would like to compute. But of course, these abstract things cannot be stored on a computer. So I need some way of translating that into the computer, and that's done via this. So that's simply a set of complex valued functions that gives me numbers. You can think about, for example, if I have matrices at input, these functions would give me the matrix values. Or I could, if my input was, say, a Schrodinger operator with a potential, it could be point samples of that, or it could be point samples of another function. It could be the initial values of a PDE, for example. To be able to talk about conversions, we need to have some understanding of distance, hence a metric space. And then the final thing here is the problem function that you would like to compute. Say that I have a matrix, and this here gives me the spectrum, or it could give me a solution to a linear program, or a solution to a PDE, whatever you want. This is a computational problem. And to solve a computational problem, we're going to define an algorithm. And your reaction might be, oh no, not another guy defining an algorithm. But this is exactly the issue. There's tons of different definitions of algorithms that will give you different notions of computability and computations. The purpose of this is to make something which is so general that if you're going to make a statement which says this is impossible for any algorithm in any model of computation, you need this kind of generality. So the purpose of a general algorithm is to have a framework that allows you to make completely universal lower bounds. You will never work with this to get an upper bound. This is only to show impossibility results. So to do that, we essentially say that there are three axioms that any algorithm will have to follow. The first one is that you only work with a finite subset of info. That info can be adapted. It can depend on the input. And we don't say how that's done. We just say that there's a finite subset. The action of the algorithm of that input can only be on that finite string. Number 1 and 2 here is completely obvious. If you don't have that, you can do whatever you want. But you have to be a little careful. If you only have these two axioms on an algorithm, you can also compute whatever you want. You need this consistency condition. And this here is essentially what replaces the standard recursivity. Recursivity is much, much stronger. And this is essentially the key part to where things break down in numerical analysis. So this gives you a tool that you can put in your Turing machine, your BSS machine, whatever you want, and everything is going to be a general algorithm. So if you show that you can't do it with these tools, no algorithm can ever do it. If you want to get an upper bound, then you put more structure on it, and then you say, here with my Turing machine, I could do it, for example. I also want to mention that the purpose of this is to make it simple. Because if we talk about foundations of computational mathematics and lower bounds, we have to define an algorithm. And most people in numerical analysis are not overly comfortable with the definition of a Turing machine, or even a BSS machine. This here allows you to do these kinds of things without essentially going into the nitty-gritty details. This is something that can be understood very simply by analysts. So that's another motivation. All right, so we cannot describe the world with simply this definition of a general algorithm. You need also what we call a tower of algorithms. And the reason why, that's why I wanted to show this example with Smale's problem, is that there are problems for which you cannot achieve unless you actually pass to several limits. So this is what a tower of algorithms is. It's simply a collection of sequences of functions for which you require this guy here at the very bottom to be a general algorithm. And then you march your way by taking limits, n1 tends to infinity, you get the second one all the way up to the guy you're actually interested in computing. For example, the spectral. And now, oh yeah, shoot.
Why can't you call this whole thing an algorithm?
Yes.
Yes.
That's the problem. It's impossible, because you could say, why can't I just re-index it? And that's impossible. That's why you have to do that. I'm going to show you several examples.
Okay.
So these examples of McMullen is one case for a specific case of this of rational maps. But even the spectral problem you have, you cannot do any indexing. That's impossible. That's why, because otherwise I wouldn't have had it. And this is actually a very good point. I'm going to get into this because sort of the understanding that we've had in classical numerical analysis that everything can be done in one limit. That's not the case. And that's a crucial part of this theory. Okay, so with that definition of a tower of algorithms, you can define what we call the solvability complexity index. And the solvability complexity index is simply the smallest height of a tower that you can build for your problem. So the smallest number of limits that's needed to get to your problem. But you have to be a little careful, because I've allowed this little alpha here, and that alpha is going to essentially describe the model of computation. If I let that to be G, which is, I'm going to call this general algorithms, then that is a lower bound. This is the best thing you can ever do. But I could, for example, put slightly more structure on it. I could require that this should be done with a Turing machine, and then the SEI might change. So we have to take care of this little guy here. We say that if no tower exists at all for your problem, then the index is infinite. And if you can solve it in finite time, so your algorithm halts and spit this out, and you don't have to pass the limit, the index is 0. So that's where computer science lives, problems that you have essentially solved in finite time. And as I mentioned, yes, please. That's what I'm going to right now. Yes. So the structure that I can put on here is I'm going to say, what is this algorithm that I have at the very bottom? And if I say that it's a general algorithm, I'm going to put a G here, and that's only used for lower bounds. I can put on more structure and say I want this to be, say, a Bloom-Shub-Smale machine, or I can say that there's a Turing machine. Those are the ones I'm going to use for upper bounds. So what that means is that the guy that I have at the lowest level now is an actual algorithm that I define to be, say, a Turing machine. And then I'm going to call that an arithmetic tower and use the subscript A in each case. In all of the examples that I show now, it doesn't matter if you're in the BSS on the Turing model, so I'm not going to specify which model I'm using. All right. So now we can define the first part of the SEI hierarchy. And there's nothing controversial in this. I simply define the delta 0 class as the class of problems for which has index 0, so the ones that you can solve in finite time. Then delta 1 is going to be the set of problems for which you may need a limit, but you have error control on your algorithm. So you'll know exactly what you're doing, and you can say, if I want this to be within epsilon accuracy, I can get it. Now, delta 2 is going to be the set of problems for which you need to pass to a limit, but you may not have error control. And then delta m plus 1 is going to be the set of problems for which you may need m limits. And there's no error control on any of them. You only know that you can pass through 1, 2, 3, and some m, and then you actually get it. And this is related to your question. There are problems that are that bad. So, but the motivation that I started with was the computational spectral problem. We're going to solve this in the end. And the first question we have to ask us, is the suggested hierarchy now fine enough to be able to describe all spectral problems? So I'm going to start with the toy problem. Suppose now that I had a matrix for which I had only stuff on the diagonal, zeros elsewhere. And I'm interested in computing the spectrum of that. What would I do? I can simply collect the elements on the diagonal, right? Yes. So what that immediately tells me is that I can compute spectra of infinite matrices that are just diagonal by simply collecting these guys, because the spectrum is just the closure of the union of this. And what it also immediately tells me is that the class of spectral problems cannot be in delta 1, because then I would need to have an error control. If my class now is of all matrices of this form, I can collect the things on the diagonal, but I have no idea what comes next. So there's no way that I can say, oh, I have computed the spectrum with accuracy epsilon. And that's interesting because it becomes immediately non-computable in Turing's definition of computational problems. Yet we're actually working with these things on a daily basis. But what we also see is that if I simply use that very trivial algorithm of collecting these elements on the diagonal, that algorithm has a very nice feature. I will never make a mistake. I will always converge to the spectrum, right? But what it spits out is never wrong. So I don't know if I have everything yet, but what I have, I know is true. That is not captured in any of these classification delta classes that I suggested before, and this is the motivation. So what you can think of here is that this is some kind of convergence from below, right? I have the full set, and I'm getting more and more and more and more and more. I don't know if I have the whole thing, but I'm getting there at the end. And I know that I will never make a mistake. And I could do a similar thing with convergence from above. So, maybe I had an algorithm that would essentially encapsulate the spectrum, and it will shrink around it. So I'll have an estimate from above, and it will converge. And both of these scenarios will give motivation for this first one. This is the sigma 1 class. This will be convergence from below. And the pi one is convergence from above. Did that make sense? Hopefully. So here, this class now is essentially of all the problems for which I will be able to converge to the true solution, but I know that what the algorithm spits out is always going to be, say, in the spectrum up to an arbitrarily small accuracy parameter. And then you can make this bigger and say, and more general, I could do the same thing for higher up in the hierarchy by saying that delta or sigma m plus 1 and pi m plus 1 is simply going to be the classes in delta m plus 2, and then where the last limit is either from above or from below. Yes, please.
I have a problem understanding what you mean by convergence.
Convergence, I'm passing to a limit, and I get there in the end.
Let's say you have a diagonal matrix with just random entries on the diagonal all
Yes.
the way down.
Yes.
Every time you stop at a finite point, you are not sort of getting closer to the thing.
But if I fix it, if I say, here is my matrix, you will agree that the spectrum of a diagonal matrix will be the closure of the union.
Yeah, but what I mean, it's more classical notion of convergence of series and so on. I mean, you're getting closer and closer to the result as you continue.
Yes, but I'm talking about the desired output is the spectrum. So the spectrum of a matrix now, of a diagonal matrix, is going to be the union of all the eigenvalues and the closure of that, since it's infinite dimensional. So my algorithm is simply picking elements in this. And as I move along, I'm going to get closer and closer to the total set in the Hausdorff metric. You agree?
In the house, yeah.
Yes. So I am converging to the spectrum. At no point will I know that I have the full thing, because I'm not God. I can't see what is happening at infinity. But what I know is that if I do this procedure for this very particular class, I know that my algorithm never makes a mistake. which is a very nice thing. Because if it just converges, I would have no idea. It could be that I'm close, it could be that I'm not. Did that make sense?
I have to think about it.
Okay. So this is how the SEI hierarchy looks like. You have the delta classes. These are the big pillars. And then if you have extra structure, like in this case, the Hausdorff metric on the compact subsets of C for the spectral problem, you can define these pi's and the sigma classes in between. If you don't have any extra structure like that, there's nothing you can do. Then these are the big main classes. Okay, so now, boring, dull, and dry things over. Now we're actually going to use it. So now we're going to see what you can use this with.
Did you assume that your spectrum was inside a compact set or something like that? Or not?
Well, it will always. So if it's a bounded operator, it's always it's always a. If it was unbounded, yeah. If it was unbounded, I have to change the metric a little bit. It's called the Autos-Wets metric. It's slightly, but let's do Hausdorff. That's something that we can. All right. Remember Arvison's frustration. What we're going to try to do now is to explain Arvison's frustration with the tools from the SEI hierarchy. And the point is that you can essentially classify all these different types of spectral problems in terms of this hierarchy. So if I think about B of L2, that's the class of all bounded infinite matrices. I'm interested in asking, can I compute the spectrum of those? I could narrow it down to self-adjoint operators. I can narrow it down to compact operators. And I can ask, where is the problem of computing the spectra of these operators in the hierarchy? And they're already here, but I'm going to show a figure that illustrates this. So this is where the general problem lives. This goes back to your question, sir. You need three limits. There does not exist any algorithm or any indexing that can actually do this. You need three limits. This is completely impossible to deal with. The only sort of sugarcoating is that the last limit is from above. This is how difficult it is. And now things become interesting. If you add a little bit of extra assumptions on it, bounded dispersion, that's just a fancy word for off-diagonal decay, then the problem jumps. And I'm going from pi 3 to pi 2. If I took this guy here now and added a slightly different assumption, namely controlled resolvent, meaning that I have an understanding of how the resolvent blows up close to the spectrum. So in the self-adjointness or normal operators, this is trivial, this is obvious. Then I go from here, and then suddenly I get a sigma 2. Jumps down in the classification hierarchy. And the beauty of this is that if you add these guys together, you should be able to jump down here, but you get a bonus. You're actually down here. And what this means is that if you have something which is self-adjoint and bounded dispersion, i.e. you have off-diagonal decay, you're in this area here, the sigma 1 class. That means that it's not harder than actually computing the spectrum of a diagonal matrix. You do have an algorithm that will never make a mistake. And this now suddenly explains Arvison's frustration. Because the common wisdom, at least in the 90s and sort of after that, was that you should have algorithms that were based on one limit. That's impossible. You can never do that. The self-adjoint problem is here. That's why there wasn't any theory for this. There wasn't any algorithm that could actually handle a general case, because it's impossible. And that's why it also took quite a long time to understand this. So when this is established, then we realize that the only way to solve the problem is to be able to add more and more assumptions on it, and then you can climb down. And this is the crucial class. The interesting thing, and this goes back to the question of just convergence. If I only have a compact operator, it's the only input that I have, computing spectra of that is strictly in delta 2. It is not in sigma 1 nor in pi 1. That means that no algorithm for the class of compact operators can tell you anything about the convergence. The only thing that you know is that it converges, but you can never know anything about how close you are in the general case. So if you want to have any assurance, and even if it's compact, you need to add an extra assumption, and the algorithm needs to use that. And similarly, you can solve the problem, this long-standing problem of computing spectra of Schrodinger operators. And here's the paradox. This problem here has been open since the dawn of quantum mechanics. But with a tiny little assumption that you need bounded variation on the potential and some growth of the resolvent, computing spectra of these operators are not harder than computing the spectrum of an infinite diagonal matrix. And ironically, pardon me?
What if you don't get this assumption?
So,
For example,
yes.
for Anderson localization.
So, if you don't have that assumption here, it's a very good question. We actually don't know completely how high we end up. And that's a very good question. We haven't cooked up a counterexample yet. I firmly believe that it's going to make a jump in the hierarchy, so we have index 2 for it, but I simply don't know. But the good news is, with that now, suddenly you can use this in computer-assisted proofs. You have an algorithm that will never make a mistake. And so ironically, computing spectra of compact operators, which are known for decades, you can just use the finite section method, that's strictly harder than computing spectra of these things that looked before completely intractable, but these are actually strictly easier, which is good news. And here is an example of this. So this is a beautiful figure. This is made by my Matt Colebrook. Here shows an example of a quasicrystal in a magnetic field. This is the strength of the magnetic field, and this gives you a Hofstadter butterfly. And if you're using the classical methods, you are essentially getting completely wrong output in the spectrum. But what you can do, because now we know what the classification is, this is a sigma 1 problem. Not only can you remove that, but you know what this is actually in the spectrum. Up to, was it 3 digits in this? Something like that. And that means that we can verify completely. So you can check your model, and you can guarantee that the numerical solution will never be wrong. And that also allows for verifications in computer-assisted proofs, which I'm going to talk about at the very end. So we wanted to check if the physicists like this. And they do. So we wrote a paper that was really targeting the physicists to see if they could understand the value of this. And they were so happy that they put it on the cover of this. So this is a June edition of PRL. And this is actually the first ever computation of the ground state of a quasicrystal ever done with these kinds of algorithms. Right. OK. So now we're going to go to motivation number 2, linear programming. So I showed you this bizarre example of MATLAB failing. And the problem that we're interested is really in the following. It is true that you can compute solutions to linear programs over the rationals. But I'm interested in computing with irrational numbers. And that's because I'm working in, for example, the field like compressed sensing. And in that case, I'm using the discrete cosine transform or the discrete Fourier transform on a daily basis. So if I have that as my input to my optimization problem, I need to be able to deal with inexact input. And of course, I'm not the first one to point this out. Smale even puts this in his list of problems for the 21st century. You need to have a model that allows for inexact input. And it's not just, I'm going to have cosine 3 as an input or e to the blah, blah, blah. If I'm running floats, a number like 1/3, which is an irrational number, or 1/10, is still going to be approximated in base 2. So I'm doing approximations all the time. Even in MATLAB, if you write 0.1, it's not stored as 0.1. It's still stored as a base 2 approximation. So I don't have to consider just linear programs. I can consider a whole bunch of other types of optimization problems where I'm interested in getting the minimiser. And if you look at this list here, modulo the problems of training neural networks, this is essentially the collection of standard optimization problem that you have in mathematics of information. And a basic question is this. Given any of these problems, if I had input now that comes with some kind of inaccuracy, so think about the input now to my discrete Fourier transform is given with some inaccuracy. I'm going to call it epsilon hat. Does there exist an algorithm that can compute a minimiser, say, of a linear program, to whatever accuracy I want. And the algorithm should, of course, be able to choose this input accuracy as freely as it wants. So I'm simply asking the following question. You have the discrete cosine transform as your A, and you're going to plug that into your linear program. And I'm asking, can you find an algorithm? You can write this down in MATLAB, use the variable precision command as freely as you want, and I need you to guarantee me that I can get my 5 digits, or 8, or 10. And is that possible? And a negative answer to this here would be what Turing would be calling non-computable. In this SEI hierarchy, it says that this is not in delta 1. And now, of course, since there's a lot of leading numerical analysts in the audience, the first reaction that you have is, well, this must be related to condition, right? Ill-conditioned things are bad, well-conditioned things are good, right? So I'm going to put on all the kinds of conditions number that you can plug in from the literature. This is not new, obviously. Condition number matrix, we all know. If I have a linear program, the matrix may not be invertible, but I can talk about AA star and look at the condition number of that. I could look at the condition number of a mapping. This is all basic in the literature. I could look at the feasibility condition number, which essentially says, I would like to avoid problems for which I take a tiny little perturbation and suddenly it becomes unfeasible, right? So now the problem becomes slightly more interesting if I say, well, if I take any of these optimization problems, say a linear program, if I now restrict myself to inputs that are completely well-conditioned, now I still ask my question, can you find an algorithm that's going to compute a minimiser? And everything is well-conditioned. And the answer to that is no. But this is just the beginning. This is actually what's going on. And this is all essentially SCI machinery behind. Take any of that problem list on that slide number 38. Say linear programming, because that's everybody knows that. Choose an integer, k greater than 2. Then there exists a domain of inputs so that everything is well conditioned and everything is bounded and nice. But you'll have the following paradox. There does not exist any algorithm that can compute k correct digits. K correct digits here will be in the L infinity norm, but you could have chosen any norm. You can not find an algorithm that can compute k correct digits for all inputs in omega. But for the same class, if you're a little less greedy, you can compute k minus 1 digits. The important part is that it's the same class, the same omega. You can't get k, you can get k minus 1, but any algorithm that can give you k minus 1 digits will spend arbitrarily long time. In other words, think of a large number. There will, say, 10 to the 80 years, there will be an input so that your algorithm is going to run longer than 10 to the 80 years to be able to get k minus 1 digits. However, you can, if you're even a little less greedy, get k minus 2 digits, and that problem is in P. So the same problem class, you go from this is impossible if you want k. You can get it if you want k minus 1, but it can take you arbitrarily long time. Getting k minus 2 is quick. This is how bizarre linear programs are.
Let me understand this thing.
Yes.
So you are given k, then you find the domain omega which depends on k.
Yes. But I should say, if I don't, so the reason why you want k bigger than 2 is simply because you want to do this k minus 1 thing.
Anyway,
Yeah. If I only worry about this, k can be 1.
No, but then you find domain
Yes.
omega which depends on k.
Yes.
And then your
Yes.
three statements is about this domain.
That, the same domain. That's the point. So what it says is that you cannot get 4 digits. You can get 3, but it's going to take you arbitrarily long time to get there. Getting 2, you can do super fast.
So then I somehow just I'm trying to figure out the paradox. Because given k, you can reproduce k minus 2 digits.
No, it's so given k.
K plus 2, and then k agency will be...
No, but then my omega changes. The point is that this phenomenon happens. I can do this for k equals 65. I can do this for k equals 3. There will always be something that's well conditioned, and you can get it fast if you want, say, 64 digits. 65 you can get, but it's going to take arbitrarily long time. 66 you can never get. That's the paradox.
The point 3 somehow. So you have k, you have omega, which depends on k.
Yes.
And then you said that you have an algorithm which produces k minus 2 digits. Yeah. On this
Yes.
omega.
Yes. But no algorithm can do, well, you can do k minus 1, but it's going to take you a long time.
Right.
And nobody will do k.
What this means that for any k and for any omega,
Yes.
there is an algorithm which produces k digits, right?
Yes. Well, no, so that it doesn't say.
No, but if it produces
It-
k
it-
minus 2 digits on any...
Not for any, because for given k there exists an omega. That doesn't mean that given omega there exists. That's a different statement. Right. Yes. Where's the alpha? Oh, sorry. My bad. It should have said 2 instead of the alpha there. It's a cut and paste from it. I'm really sorry. Yes. You can have a uniform bound on all of these things, and that's the whole point. Because everything is restricted. Nice and very good that you pointed that out. That's what happens when you do cut and pasting 10 minutes before you give the talk. Anyway, so
But then
yes.
Okay, so for any k there is omega k, on which k digits are just impossible to attain.
Yes.
It's possible k minus 2. Does it mean, do you have a kind of negation that for everything else except this omega k, everything is fine?
No, that's the point. So it can be what it says is that it can be arbitrarily bad at the same time as it's not as bad, because you can get k minus 1 and k minus 2. That's the paradox. That's the...
But still, I mean, in any case, there is some bizarre domain of inputs, yeah?
Yes.
Which is probably outside just everyday life is completely, yeah.
The example that I showed you is exactly in this. This here is exactly that. This here is the theorem in practice. This is why it fails. And now you're going to say, so I'm going to ask you, can you spot what is going on? Because this here, it should be fine. I should be able to do everything exact. So what you could have said, oh, but this isn't exact, because actually if you implement this in MATLAB, this is going to be approximate base 2. If I change this so that was actually a base 2 thing, it would still get the same results. And now we go like, why? The point here is that you're still doing a round-off. So if you do the backward error analysis on this, you're still getting a slight perturbation on your input. It's equivalent to that. That's why you're getting this. But what the theorem does not explain is this. Why does the exit flag give you wrong things? Because you could potentially be able to check if an algorithm makes a mistake. You won't be able to correct it, but you can say this is wrong. So why do you get this? Because the interesting thing is that if you plug in a linear system, which is ill-conditioned to MATLAB, it immediately detects that. It gives you a warning. It says this is a bad thing. Why is MATLAB certifying the nonsense as correct? And this is not easy. This is very deep. This problem. Oh, pardon me? Say that again.
Did you contact Matt?
We will eventually when the paper is out. Yeah, shoot.
You said that even when you have 2 to the minus k, you're still doing a rounding. How is that so?
No, so the algorithm in this case here. So yeah, that's a good question. Okay, so if I implemented this here, and if I implemented this here with a simplex algorithm, and everything is fine, with this, you're going to get the same nonsense. If I actually do simplex with interval arithmetic, you're going to solve it. Absolutely. I'm not disputing, well-known facts. What is happening when you're doing this? This is actually an interior point method that tries to solve it. What is happening, even if I plug in here 2 to the minus k, so a base 2 approximation.
Oh, okay. Yeah, I misunderstood. I think you said there was rounding taking place on the second line.
Yes.
Rounding taking place inside line
It happens inside. Yeah, so what if you did the backward analysis, essentially that boils down to a tiny little change in the input. That's what happens here. The point is that this is not explained. So is this because Cleve Moeller hired incompetent people? It's much deeper than that. So first of all, that is also impossible. But here comes the beauty, and we have to admit we're a little proud of that, because this problem here is actually strictly harder than computing the solution to the original problem. So what MATLAB is doing here, in the inexact sense, is completely impossible. What is doing here is impossible and harder than doing that. And this is the whole SEI machinery going on behind. Right, how am I doing on time? Because
It's running fast.
pardon me?
You should finish in a few minutes.
Few minutes? Yeah, no, that's running pretty fast. Because I want to mention, yes. Anyway, I want to talk about computer-assisted proofs and the role of the SEI hierarchy. If you're interested in foundations of computational mathematics and also what's going on in pure mathematics, we're living in very exciting times. Because there seems to be now a change of paradigm in pure math, for which high-level pure mathematicians solve a very big conjecture with numerical analysis and scientific computing. They're computing things with inaccuracies, and they solve big problems. And this is very exciting. I'm going to talk a little bit about it. So I'm going to take two examples. One is the Kepler's conjecture solved by Tom Hales and collaborators, and the other one is the Dirac-Schwinger conjecture by Charlie Pfefferman and Louis Secco. Hilbert's 18th problem, or 18A is actually more accurate, says this is the optimal packing of snowballs. Tom Hales submitted a paper in 1998 on this. It was published in Annals in 2005. It was called The Proof of Kepler's Conjecture. It was published despite the fact that the jury only were 99% sure that the proof was correct. So it ended up being sort of the proof of Kepler's conjecture. So Hales continued with a whole team, they called it the FlySpec program, to do this formally. Both in the original submission and the final one, which I'm going to comment on in a second, it's a fantastic, it's a stellar proof. If you're interested in foundations of computation, this is a delight. What they're essentially checking are 50,000 potential counterexamples to the conjecture. And the way they're doing that is by checking linear programs. They have 50,000 linear programs, and they have m here is an irrational number. That's a fixed irrational number. And they're running 50,000 linear programs, and they have this decision problem here. If this is true for all of them, they're good. Tick the box. That would have been completely fine if you had rational inputs. But given that this is a packing problem, the fact that you're getting pi is not going to be a great surprise. So what do? I just showed you a pretty bizarre result, saying that what happens if you try to solve linear programs with irrational inputs. So what they're doing, first of all, you don't go for this directly. You go via the dual. Because if you have the dual, then you can only find a candidate for which this is true, and then that immediately decides this. However, since this is done with inaccurate calculations, you essentially compute this here to the kth digit, and they need 6 digits in this. But is this so straightforward? Not completely, because you can show bizarre phenomena here as well. So for that particular problem here, which is exactly what they're doing in Kepler's conjecture, you can have the following. Choose a k tilde greater than 1. There exists a class of inputs so that the problem, and this is this one here, with that k tilde, a k being k tilde, is not even in sigma 1. That means that even if the statement is true, there does not exist any algorithm that can verify it. So no algorithm would be able to actually tell you if this is true, even if it was. At the same time, if you're a little less greedy and you do k tilde minus 1, that is actually computable or decidable. So this is how bizarre these phenomena actually are. So what they're doing is that they're actually creating an algorithm that does all the approximations. And the domain of that algorithm will give you a sigma 1 classification. That means that if the answer is true, the algorithm will halt and give you yes. If the answer is no, the algorithm is going to continue forever. That's what they did. So implicitly what they're doing, they're proving this classification result in the SEI hierarchy. They don't mention it because that didn't exist at the time, but that's what they're doing. So a crucial part of Kepler's conjecture is actually getting that right. And this is incredibly delicate. And what could have happened is that if one of these guys here were no, the FlySpec program would have continued forever and not concluded. And you would never have been able to prove Kepler's conjecture in that way. But they get 50,000 yeses, and it's there, and it's rock solid. And it's now published. It was published in May 2017. It's an absolutely stunning result, the actual proof. Very quickly, going to run through, because Brynjolf is, I'm suggesting I'm running out of time. If you're interested in mathematical physics and computer-assisted proofs and actual numerical computations, this is an awesome proof of the Dirac-Schrodinger conjecture by Pfefferman and Secco. This is about the asymptotic behavior of the ground state energy of an atom. And I just wanted to say what they do. They have, it's done over, I think in total 8 papers, so it's about somewhere between 500 and 600 pages of math with a lot of computations. One computation that they're doing, they're solving this boundary value problem here, and they're desperately interested in getting that guy, the derivative of the solution. And they're also interested in getting, for bizarre reasons, the first element here in the series, the B1. And this is exactly what they do. This is how this is translated into the SEI hierarchy. These are the statements that they make. Given a representable W, this is a number that you can produce on the computer. The decision problem is to do this on the W0. And the same thing with the B1. And the point I want to make is essentially that these are just classification problems in the SEI hierarchy. So I'm going to wrap up. There's tons of stuff that you will see with the SEI hierarchy in different areas of mathematics. I could have gone on with this list and talked about PDEs and foundations of computational mathematics in general, but I'm running out of time. So with that, I thank you very much for your attention.
All right, maybe just to add some other problem to Kepler conjecture to check whether it's working or not. So that the prime number theorists are working on this twin primes conjecture.
Yes. Yes.
They are using
How close are they now?
I think so. Well, it was 600 something like 5 years ago, and then.
And the original was millions, right? Or
10 million.
yeah. Is it 6? Yeah. All right.
Now it's 6. Yeah.
Wow.
Because I thought one of the Massinos told me that it's 100 now.
According to Vicky Neal, it's 6.
6. But they're using numerical analysis. I don't know to which extent, whether it's at least for 600. Yeah. So
It could be. I don't know if so number theorists do this, but there's a difference between traditional computational number theory, for which they actually do with integers. But the solution of the weak Goldbach conjecture, which is a big thing now, that's actually done with numerical approximations. So
no. The point is that numerical approximation was used at least just for these 600.
It was used. Okay. Great. Yes.
You may check as well. It should not be dismissed. Yeah.
Indeed. Yes.
Maybe it's a fast fetch, but in your programming, it's known that there are certain instances that typically provoke long runtime with algorithms.
Yes.
Such as simplex method.
Yes.
But these instances are known to be unstable.
Yes.
So you shake the input a bit and
That's true.
Runs fine again.
Yes.
So does your research kind of touch on this?
It has absolutely no relevance, and it's not because this is the Spielman stuff that you're the smooth complexity stuff. Beautiful stuff. It has nothing to do with this, because now what you're what those results say is that yes, but I still have an input which is rational. So simplex runs in exponential time. That's fine, but here I have irrational input or inaccurate input. So in that case, none of these complexity estimates would make any sense even. That's the issue, because the complexity estimate is in n and l the number of bits. So it's true, yes, you run an exponential time there, and then you can take a tiny perturbation, but you take a tiny perturbation of your rational number with another rational number. That's the issue. And then, but here, I have pi as input. And so the L in there is infinite. So it's a good point, but the answer to your question, they're not related at all.
Okay, I think I shall need a little bit of time to digest all this, Anders, but thank you very much.
Thank you.